Welcome everyone. Welcome back everyone rather to Cybersecurity with Python and the Microbit v2.0. This is workshop day 2 of 3. Today, I think I'm going to go back and revisit a couple of things that I might have not quite gone as deeply into as I should have on Monday. A couple of the computer science concepts that we'll be recycling today in the cybersecurity portion. The main focus of today will be the cybersecurity portion. That's going to be encryption, sniffing attacks and defenses, brute force attacks and defenses, and this is not correct. We'll probably make it all the way through brute force, and then we'll be doing malformed packets on Friday. On Friday, this is not in stone yet. I'm going to try to get someone from cyber.org to talk with us about some of their offerings. We'll take a look at how some of the cybersecurity materials are used with the Cyberbot robot, which has a microbit in it. And we'll look at educator resources, talk about upcoming workshops, how to purchase the various materials that are used in this curricula, questions and answers, and wrap up, and that'll be it. There will be some homework. I'm not sure what it'll just basically I'll pick that on the fly depending on how far we've made it through the material. Okay, and let's see here. And so also, please feel free to jump in with any questions you might have, either simply unmuting yourself and saying, hey, Andy, or chatting Stephanie. And either way is good. And now I see why that wasn't right. I was on the wrong slide. Sorry about that. Okay, so as far as review and recap goes, the first thing I'd like to talk about is the dictionary primer. So we talked, or I said on Monday that we have a dictionary, and a dictionary is typically enclosed in curly braces. I don't know if those are showing up really well, but those are.
It's pretty clear in the illustration of the dictionary primer.
Okay, so you're able to see this right here as a curly brace?
Yeah.
Okay, good. So these are curly braces that contain a dictionary, and a dictionary is some number of key value pairs. And here we have two examples. The key is to the left of the colon, and it has some kind of name. The value to the right of the colon is whatever data you want to have corresponding to that name. And then here's another key value pair with score. And instead of a string like Sir Lancelot, we have the number 1000. You can add and remove entries from dictionaries. And for example, if you want to find out what value corresponds with score, info is the name of the dictionary. In this case, we said info equals and then the whole dictionary. So you can say info of and score. And what this will do is it will return the corresponding value to the score key. And then that result will end up getting stored in number here. You can also change the score simply by saying info of score equals and then a new value. So that's a dictionary. And the thing that's really useful about dictionaries is it removes, aside from the fact that it's essentially JSON data, which is the kind of data that goes back and forth all over the web between browsers and servers, and it's also one of the reasons it's so useful and can be used that way is because the order doesn't matter. There's no big onus on keeping everything perfectly organized here. Down at the lower level in the electronics world, oftentimes you'll see a series of byte values, and there'll be something that states that the 5th and 6th byte correspond with one thing and the 7th and 8th byte correspond with the other. It's really easy to make mistakes, very difficult for students to program to have, one microcontroller exchange data with another if they don't have something like a dictionary at their disposal. The dictionary makes things much simpler, in addition to being a good lesson about essentially how things work when it comes to exchanging data over the internet. So here is a quick little example that we can talk about. And I apologize, I forgot to tell everybody, okay, we want to make sure that you've all got your 2 microbit modules connected. I'm going to go ahead and connect mine right now. And what I'll do is I'll just demo this instead of having you guys all do it. So it'll give you some time to get connected. All right, so I just plugged in my 2 microbits, and then when I hit connect, I get 2 options. Again, you want to choose one option in one copy of python.microbit.org/v/2, which is just about in your chat. Okay, so there's a chat of the address. So python.microbit.org/v as in Victor /2. And so go ahead and get both of your microbits connected, and remember to connect to a different instance of the microbit on your second copy of the browser. And many of you will want to keep your 2 browser tabs in the same browser so that you'll have room over on this side to put the Zoom meeting. And again, with that, when you are if your Zoom meeting is filling the entire screen, there will be a view button over here that you can click and select exit full screen. Then you can resize it and put it on the left side of your monitor if you only have one, and then put the 2 tabs of python.microbit.org editor on the right side. And also give me a shout if I've let if it's too small to see, and I'll try to zoom in on any detail you might be interested in. So back to 38, this is just a few different things you can do with dictionaries. And so I'll go ahead and paste that in. Flash it, and then open the serial monitor. And I have some stuff from the program that was previously running, so I'm going to close and reopen. And then it nicely starts from the beginning. And so essentially it's saying that the dictionary in this case is name and Sir Lancelot, and score is 1,000. And here we asked it for the score and it gave us 1,000. We changed the score to 2,000. The students get to see how that affects the way the dictionary looks. So a statement changed the score to 2,000, and I'll get back to this in a second. So they can see that the score is 2,000. We're actually adding a field here to the dictionary goal of 5,000. So if we go back and look at the script, so here we are with the original dictionary named info. we printed the dictionary. And in doing so, we can see it shows us the contents of the dictionary. And remember that print sends it to the serial monitor here, serial terminal. Then this print statement just looked at the score key and grabbed the value, which is why we saw 1,000. Then we print, hey, we're going to change it to 2,000. Info of score equals 2,000. Print info. And that's where the students get to see, oh, look, score changed to 2,000 in the dictionary. Then printed that we're adding a goal. And so info of goal equals 5,000. So that's like we're keeping score. And so we're waiting until the player reaches their goal maybe. And so here we have the goal of 5,000, and simply saying this, even though info of score existed and it just got changed, info or score, the score key and its corresponding value already existed, and this just changed it. But if it doesn't exist, dictionary name of key field equals value will end up just automatically getting added to the dictionary. And so now we have goal, score, and name. And you might notice that goal was just inserted here. The one nice thing about dictionaries is that the order of the pairs doesn't matter, because the key and its corresponding value will always travel together. But these guys might be over here. This guy might be over at the end. And those kind of things don't matter, because it's going to get found when you use a statement like give me the value that corresponds to the score field. Okay, how's that? I hope that if anybody was feeling at all uncomfortable with dictionaries, I hope that kind of clears a few things up. As always, feel free to jump in. I'd also like to take a slightly closer look at strings. We talked about strings on Monday. And so we talked about, hey, if you put it inside quotation marks, it's a string. A string is a sequence of characters, and strings have features that you can use to manipulate their contents, change what they have, find things within strings. And there's an entire chapter about it, just as there was a chapter about dictionaries, and there's also a chapter about exception handling. And so if we take a closer look at this, I think this was from the optional homework. So here's an example of some of the introductory material about strings, and it explains, hey, look, you can have a string with single quotes or a string with double quotes. And if you use either 3 single quotes or double quotes, you can have a string that goes across multiple lines. Strings can also go across multiple lines using the / character after them. And let's see. And next up, I'm looking for, here it is, features. All right. So looking at a string, if you give it a name like S, it has a 0th character, a 1st character, 2nd character, etc., all the way up through the last character, which in this case is the 11th character. So here is an example where S of 6, so that's this string right here, S of 6 will go to the 6th character, grab it, and sadly it's an S. I don't exactly like that. Wish I'd done that a little bit differently. And so that S will get plopped here and then copied over to C. And when you say print C, you'll see the value S. And this page also talks about things like there is a function called ord, and that returns the ASCII value of a character. That's the number that corresponds to a given character. There's also CHR, which would take that ASCII value, that number, and give you back the character it corresponds to. Length will tell you how long the string is. And if you have a number like 1, 2, 3, 4, you can put it inside str with opening and closing parentheses, and you'll get a string that contains the characters 1, 2, 3, 4, as opposed to an integer which might contain the value 1,234, or 1, 2, 3 would be another possibility. And so this is what this does is it shows even more options about making all the characters uppercase, lowercase, and so what I have for you is a pre-written program that has all those little features in one shot. And I'd like you all to go ahead and run it. Hopefully your microbit modules are up and running now. So we'll go ahead and paste that to you. There you go. Close serial. Select all. Whoops. And so those are the results of things like string.find, and then string.find sequence. And so what it will do is it'll go and find sequence, and the S in sequence, it'll say, okay, how many characters is that over from the 0th character? And it'll actually tell you the index of that character. Car list will give you a list of individual characters from within the string. String.lower will give you a lowercase version of the string, string.upper an uppercase version. And then we can take a number, and then and in that case, the number, we started with S up here. 1, 2, 3, a string of characters, not the number 123, but int of that string gives you back 123, the number, which gets plopped into n. 1 was added to n, and that's why print n here showed us 124. So here we have the number 124. Here we have our uppercase, our lowercase, our sequence of individual characters, the index of where the word sequence started at the 27th character, and then just the string itself. So there's a lot of cool things that Python has built in for doing with strings. A string is an object, and so anytime you see string.find, well, that's the string object's find method, and it's going to go and look for the sequence, or for the word sequence for you. The replace method, where you can have a new string and you can replace the word it with a string, and it'll go and find all instances of it and replace it with a string. So lots of cool things that can be done with strings, and those become important for the basic encryption examples, which is why I wanted to revisit that briefly. One more thing to revisit, which is exception handling. So again, with exception handling, the two required pieces of checking to see if some code's going to crash, and in the exception handling chapter, denominator is changed to 0. And when you try to divide by something by 0, you get infinity. That doesn't work out. So changing D to 0 causes this statement to throw an exception. And the required elements are simply try and except with a colon. Now this except exception as E is a nice feature in Python where instead of having it throw the exception, stop running, display it on its little display, and then not respond to anything until you restart it, except could just potentially do something for you, or except exception as E will actually show you the text of the exception without having the microbit halt execution. Else is something that you might want to do if there's not an exception, and finally is something that you would want to do regardless of whether or not there is an exception. But again, the two required parts, it's a try except block or a try except statement, and so you'd want to try some Python statements and then do something if there's an exception in this part. And you could have as little as just except and the colon. And so that is strings, dictionaries, and exceptions. And those are things that each of them has a chapter. So if you're feeling like that's a lot of information, that's reasonable. What I'm trying to do is part of what I'm trying to do is just make sure that you get to see some of the highlights of each chapter. And then if this is something you want to use, going through each chapter with more detail on your own is going to be very helpful. All right, are there any questions before we move on? All right, just remember, you can always jump in either with the chat or by unmuting yourself. We also did radio basics. I will actually talk just a little bit about something I forgot to talk about. In radio basics, we take a look at the antenna on the microbit. It looks a little bit different on your microbit version 2, but you'll see a similar squiggly on the underside. And it explains the radio's frequency, how that relates to the kind of radio waves it uses. You have an option for different channels. Those are different radio frequencies within its 2.4 gigahertz band. And so you can pick channels 0 to 83. And the nice thing about this with students is you can have them pair off and each grab their own channel. And I usually also recommend, for example, if you have 10 groups of 2, you might want to have the first one at 0, the second one at 9, the third one at 18, and all the way up through 81. And that'll give you 10 different channels that are well separated from each other. And so this is just some general information about the radio that I wanted to share. And then we did bidirectional text. So we all tried chatting back and forth between our 2 microbits. And again, that went into the terminal through the USB cable to the microbit, out the radio in the other microbits radio, back out to USB and onto the receiver's terminal. And then you can go back and forth where one's the receiver and one's the transmitter. And that's why we call them transceivers. We also talked about radio data, and in summary, all that radio data really is sending a dictionary as opposed to just some piece of text. Like these are just sending strings back and forth. And this is differentiating a simple string from data by just explaining, hey, we're using dictionaries here instead of plain old strings or values. And then this hopefully will look familiar. So this was the one where we split up the countdown timer over 2 microbits so that 1 microbit allows you to enter the countdown, and then the other microbit actually does the counting down. And you could actually use this kind of thing, for example, to automate model rocket liftoffs. And on to encryption. And so now I will just check one more time that concludes our computer science overview, or the overview of the computer science component. Now we're moving into the actual cybersecurity component. So again, one more call for questions. All right.
You can unmute or chat them to me.
Thank you, Stephanie. So let's start by looking at encryption by hand using the classic Caesar cipher. Here is an example. How does that look? Can everybody see that okay? All right. If we want to send the string hello, and my understanding is that this is actually something that Caesar did use, was they said, okay, well, if I want to send the letter H, I'll take that H and I'll count over some number, and that number is considered the key. And so my plain text, if I want to send hello, I'll take that H and then count over. If my key is 5, we'll count over by 5 and use M as the character in the ciphertext. If I want to send the E from hello, again, count over 5, take the J, and now we have the ciphertext. And this made it a little more difficult to, for if intercepted, it made it more difficult to figure out that the actual message was hello. And here we have the students' challenge to decrypt. And in the case of decryption, simply go 5 in the opposite direction to get back to your H from your M. So you start with M, you go back 5, get the H, start with J, go back 5, get the E. And then there's a tricky little thing about wrapping around. So what happens when you get to X? Not surprisingly, you'll count 1, 2, 3, 4, 5, and use the letter C. So that is an introduction to the Caesar cipher by hand. And then the next thing to do is say, hey, let's use those ASCII characters, those numbers that correspond to letters. Oh no, I'm sorry, we do that later. this is a really slick thing where we instead use the find method to go looking for the letter and get its index. And so this is a pretty cool program. Let's just try it. All it does is start with a hard-coded letter M and then gives you the encrypted result if you're using 5. Copy. All right, so let's try this out. I just pasted it into the chat. And I didn't quite do that right. There we are. Flash. And so I predict that M, N, O, N is 1, O is 2, P is 3, Q is 4. So let's hope it's R. Flash. Yes, it is R. My arithmetic often fails when I'm presenting, so I was worried. So it says, hey, we found the letter M. Its index is 12. We'll go ahead and add 5 to that for an index of 17. That's index equals index plus key. The part where it wraps around, basically, if you take the remainder, if you remember back to long division, where you had an integer answer and then a remainder. The nice thing is if you take the remainder of dividing your index by 26, like let's say your index is 27, you divide by 26, you get a remainder of 1. So it just wrapped you around to A. And so that would be the same as this part right here, where we're wrapping around to the earlier part of the alphabet. So in this case, the remainder would have been 2. No, yeah, 0, 1, 2, and it would have taken you to C. Did everybody get that running? Can I get some thumbs up? Thank you, Kevin. Looking good. Thank you, Sarah. Excellent. Nada, very well done. Okay, so make sure to give me a shout out if you need a little bit more time to get it running. Now, also introduced here is how to decrypt it. Let me see if I can find that. So we're encrypting a single letter. So this was the encryption. And then here we go. So one of the features that we try to build into these tutorials is to start students with a working script, something that they can have a little momentum with. So if it works right out of the gate, that's good. But we also like to have the students put their hands on the keyboard. And so here we're saying, all right, change the key to -5 and change the plain text letter to R to see if you can get back to the original result, or to the original plain text of M that was, so basically we went from M to R, and so now we want to go from R back to M. And so what I would suggest doing is changing this to R, changing the key to -5, and then flashing, and we'll see if we get from our ciphertext of R back to M. Yep. So now we started with R and we got the original letter M. Here is a terminal version of this. Okay, I'm pasting this in so you all can try it, and I'll go ahead and demo it on the screen. Close serial. So what we're doing here is grabbing characters, individual characters, so we can say H. Oh, and look at that, I threw an exception because there's no exception handling in some of these programs. We try to keep them as simple as possible, and the exception handling can make it a little bit visually confounding if you're trying to focus on just one little aspect. So make sure to use capital letters. So we'll enter a key of 5. So HELLO is going to be MJQQT. So I'm going to do capital H. And when I hit enter, get the result of M. Capital E, hit enter. Oh, I was supposed to enter the key again. Now you can actually restart your microbit from the terminal. This little Control D to reset. Don't hit Control D, just click this little oversized button here and it will restart your script. So my key is 5, and now we'll do E, and we want to get J, and there we go, we got J, and if we did LLO, we'd get QQT. What I'm trying to highlight here is that we have a stepwise process building from a smaller application to a larger application. And the students get to learn about next applying it to words. And so here is the example that applies it to a word. I just pasted that into the chat. Flash, open serial, enter the key, 5, enter the characters, make sure to use caps, and there we are. And I may have, I don't remember if, so here's the hello result, and then we could, or pardon me, here's hello typed in, here's the MJQQT result, and then we could enter a key of -5, which the students are prompted to do, and then MJQQT, and we get back to hello. And so this introduces the fundamental and a classical approach to encryption and decryption. Then in ASCII, and then we do it in a function. We talked about functions on the first day and how you can pass a value to a function. It'll do a job. It'll give your script back the value. And then we do a function for the ASCII cipher. And then this one gets reused considerably in future chapters. So here is the ASCII cipher example. And all the difference between Caesar and ASCII, that they work the same way. It's just that ASCII, this cipher is using all the printable characters as options. So the Caesar cipher, you can't use a space. You can only use the list of capital letters. Here, the ASCII cipher allows you to use every printable character on your keyboard. There is the ASCII cipher for you in the chat. And we'll go ahead and run that one just to show you how it works. Quickly, here is the ASCII cipher function. When you call it, you'll want to say ASCII shift, give it a key and some text, and it will take a look at the ASCII character using ORD, which was mentioned earlier as the way to get the number that represents a given letter, like capital A is character string 65, or is the number 65, capital B is 66. Think lowercase a is 97, and it goes up from there. And basically, by getting the number that corresponds to the letter, then we can do a little math to do all that that shifting. And instead of %26, we're doing %94 because there are 94 printable characters. And so that allows us to wrap around like we did with the Caesar cipher as well. And then after converting it to a number, it converts it back to a character, takes the number and converts it back to a character, puts that in the result variable, which is returned to the main script. So the key part here, though, is ASCII shift. That's the name. You give it a key and some text, and it will give you back the resulting ciphertext. So then looking down here, that function is called right here. And first of all, the terminal asks you to type in the text. Then, and that text is actually the key number. And then it takes the integer value of that text and gives you back the key. Then we have another input statement where you're prompted to enter some printable characters. And then that's when it calls the ASCII shift function, which gives us back the string of characters as ciphertext that you sent over as plain text. So let's take a look at how that works. And by the way, before I do, I just want to emphasize that all of what I said is also written in here. So I'm just kind of quickly going over it because, again, this is somewhat of a survey. Let's see, did I remember to paste that to you guys? Probably not. Copy. Paste. All right, Flash. Open serial. And we can certainly do 5 and try hello again. This time we can even do it with lowercase. Notice that we're still shifted over. Now, let's work backwards. Let's use MJQQT and make sure we can get to lowercase hello. and I caused an exception again. Again, we're trying to keep the script simple, so that happens, it's all right. You can just restart your microbit here. Okay, so enter key -5 MJQQQT or lowercase MJQQT. And I did it again. -5 M lowercase MJQQT. There's lowercase hello. Now, if we did a larger value, like, let's see, I'm thinking that maybe, let's try 15. If I do lowercase MJ, or no, let's see here. We'll try hello. Yeah, look at that. We have some other characters that aren't even alphabet characters. Couple of curly braces there. Oh, sorry. Oh, that's interesting. For some reason, it didn't give me the last character. Maybe it's a space. That would be interesting. -15. WT brace space. Yeah. So that was a little bit of freestyling, and of course students will try to experiment with this, and I encourage them to experiment with this kind of thing, and develop a hypothesis of why something didn't work the way they expected it, and all that good analytical learning experience stuff. So that the last thing in the encryption intro is substitution ciphers, and this is an example of taking a cipher and making it much more difficult to figure out the key, because in this case, the key is that we're taking an alphabet and we're mapping every character to a cryptobit. Now, this cryptobit, this reverse alphabet, is not the only way that it can be done. You can actually take, characters and really just completely scramble this alphabet, and that will make the cipher considerably stronger. And so that's, and again, I mentioned that we start with a working example. So here's the working example. Talk about how it works, and then challenge the students to make up a custom cryptobit, a custom alphabet, so that A might map to something like 6, and B might map to the letter J, and C might map to that parentheses or that curly brace. And that's a much stronger form of encryption that they get to try out by creating a custom cryptobit. And so that's a look inside how we're using the microbit to introduce kind of the basic idea of encryption, and along the way, getting to apply many of those computer science lessons that were learned in the computer science portion of the lessons. Next up is cybersecurity sniffing attacks and defenses. And interesting. I didn't put a link in there. Usually I put a link. Oh, there it is. Yeah, I put a link in the tile. And so you can even click the tile and go to the cover page. And so this basically talks about how you can use encryption. The whole chapter is seeing how somebody could do a sniffing attack, which is nothing more than silently listening to the communication and gaining information from that communication. and how to lock it down with encryption using the encryption techniques they just learned. And here is one of our repeatedly used applications, the countdown timer. Again, distributed over the radio network, but this time also encrypted. So, so it's not showing the encryption here because it's showing that a receiver can see it and a second receiver would be able to see all that plain text as well. But before we get there, we'll start with an application that sends some emoji. And so I'm going to paste you in the transmitter first, and then the receiver, and this is all unencrypted. Okay, I want to make sure I got the transmitter first. So here's the transmitter. This is a new chapter, by the way. The sniffing attacks and defenses is a separate chapter. So the encryption chapter ended, and now we are basically extending that by explaining how sniffing attacks work and how encryption is used to defend against it. So here is the unencrypted version. And so I want to use two separate windows now to demonstrate this. You can still keep yours together if you like. Actually, I think I may be just demonstrating using the camera for this one, and then we'll be demonstrating using the terminals in the next. Select all, paste. That's the receive. I want that on the right. I'm going back to get the transmit. Both of them are already in your terminal or in your chat. Okay, so here we are sending happy, sad, and angry from one microbit to the next. And so we can see / open serial. Okay, so we can see now that that we're sending happy, sad, angry, and happy, sad, angry is being received by the other microbit. And so one microbit is just silently sending. That's the transmitter microbit. It's not showing you anything, but the receiver microbit is showing you that happy, sad, and angry images. And then it wraps back around to happy. And the thing I want to emphasize is that normally you'd have a third student who was and a third microbit that's monitoring it. So right now, your receiver microbit is playing the role of both the intended receiver and the sniffing attack. And so here we have the 3 microbits, the transmitter, the intended receiver, and the sniffer. And so after an explanation of how it works, we move on to share something personal encrypted. Now, what's going to happen to the sniffer is actually, since the sniffer gets a bunch of garbage, the sniffer will end up throwing an exception error, while the intended receiver will still happily get the intended messages. So let's first imagine that we have a 3rd microbit that was already updated. And so we're using the Caesar cipher for this one, just as an example of using a weaker form of encryption. And then that kind of continues through into brute force, because it's easier to brute force attack a Caesar cipher than it is to brute force attack an ASCII or a scrambled alphabet cipher. So we start with something nice and easy. And let's see here. Copy and paste into mine. And then paste into the chat. Okay, so this is your new transmitter, and we're not going to change the receiver, just the transmitter. And so if everything works right, here we have our receiver, or we'll call it our sniffer. And our sniffer is seeing all these messages the same way the intended receiver is. Now, when the intended receiver, or when the transmitter and the intended receiver update to use the Caesar cipher, what's going to happen is that the sniffer on the right is going to crash. And the reason is because there's no image that we have images in the microbit that correspond to happy, angry, and sad, but we don't have any image that corresponds with KDSSB. And so that's what caused the microbit to throw an exception. And you probably guessed that even hackers are going to want to improve their ability to sniff. And so knowing that display.show choked on an image, they can simply comment out display.show. And that's what the activity does. I'm just trying to get us through this into a break, because I wanted to do one at 2 o'clock, running a little behind schedule. So now that we're not displaying anything, and we could have used try except here, but we'll just comment out display.show. And that's sad, angry, happy, sad. And so now the sniffer is no longer being foiled by their own script, and they're silently watching the communication, but still scratching their heads because it is encrypted. And after the break, we'll do a similar thing with texting with terminals, adding encryption to that. But right now, what I'd like to do is take a 7-minute break. We'll make that an 8-minute break. Have you all back at 10 past the hour. I will stick around for any questions, comments, tech support. We can do those kind of things if you're stuck on anything. But also, use this time in case you need to respond to any texts, use the facilities, etc. So be back at 10 past the hour. It is now 1 past the hour on my clock.
I will be keeping the recording going in the meantime.
Thank you, Stephanie. Stephanie, can you think of anything that I might have skipped or not talked about carefully enough at this point?
Nope, I think we're doing fine.
Oh, good. Thank you. Let's see here. Yeah, so it looks like we'll probably make it, I hope we'll make it all the way through the brute force attacks. So after the break, we'll end up talking about texting with terminals. Better take a quick look at that, make sure I remember how I wanted this to go. Okay, so the instructions probably say to use the original. But what I'll do is just use a key of 0. All right. And then there's the app data. Okay, then we'll jump to brute force. Yeah, it just occurred to me that me checking around and making a few mental notes during the break may may cause, I should have unshared my screen, might cause some confusion for anybody watching who wasn't able to make it today, because they might think their audio just went away. Regardless, it is now 10 past the hour, so I'll go ahead and continue. First off, before we get started, please feel free to either shout out or text any questions you might have. So we just finished taking a look at how there's kind of a cat and mouse game with sniffing attacks of trying to see unencrypted data, and that a sniffing attack can have trouble with encrypted data. And we'll get back to that in brute force attacks shortly. Next up, texting with terminals. This is another one of the applications that students might want to protect their data. And so we'll go ahead and start with okay, so I'm going to take the transmitter here. Let me show you what I'm about to do. Actually, wasn't going to do this, but I decided it's important. Okay, so what we'll do first is go back to the original application, and that was Radio Basics, and it was texting with terminals. So let's go ahead and I'll go ahead and paste in the bidirectional text. And this is one that you'll be using in both microbits for bidirectional text communication. We did this one already. We're going to restart with it. So I'm going to have you take this and paste it into both your online editors, and then flash it into both your microbit modules. Okay, so I've pasted the script that is in your chat log. I've pasted into both editors, and now I'll flash it into both microbits. And then we want to test it by clicking Open Serial. And if you want to get rid of the previous programs that were still running, go ahead and close and reopen Serial. And then test and make sure that the chat over the radio between the two microbits is working for you. All right, so it looks like we can have a great conversation between the two microbits, but it's unencrypted. So somebody with a third microbit would see all the same things that the two microbits have exchanged. They'd see both the ones that this microbit transmitted and the ones that this microbit transmitted. It would show up in a sniffing attack because it's plain text. All right, so that was the original one from the radio basics chapter. Now oh, sorry, go ahead.
Sorry.
Mhm.
So if the third microbit on there, it would just receive all of the text that it
Yes,
was
yes, Kurt, it would
right.
essentially see the same thing that these first two see.
Right. They wouldn't see any send unless they actually sent something.
Yeah, so the idea of a sniffing attack is that you have a silent third party who's collecting data for usually nefarious, well, I guess that depends on how you look at it, sniffing attacks of, that are in the national best interest are not necessarily nefarious. But yeah, it's we have, two parties that are trying to maintain a private conversation, and then a third party that can see all the same stuff. And that would be on the third microbit, yes. And so what we're going to do is assume first that that one of our microbits is that third microbit. And we're going to assume that the first two have decided to encrypt their data. And so what we'll do is we'll take just one of your microbits. This might not paste into the chat. Let's see if the chat will let me paste the whole thing. Ah, it did. All right, so go ahead and take what you have, what just came through on the chat, and paste it into just one of your microbits. So I'll close serial here on the left, select all, paste, flash, and reopen serial. And it's a little bit different now. The first thing it asks you is to enter a key. Now, one thing that we wouldn't normally want to do in a classroom is enter the key of 5 and then type the text hello. But for the sake of example here, that's what I'm going to do. And note that we typed hello here, and then MJQQT showed up in the sniffer's terminal. And of course, what that would cause somebody mounting a sniffing attack to realize, who's been going through the material, is, oh, look at that. They just said hello with a key of 5. I got these folks figured out. So that would be something not to do. So you could instead restart this, close serial, open serial, and we'll enter a key of 17 again. And then here is our, oh, that's interesting. I thought that we'd get a space there, but it looks like not. I'll have to try to figure out what's happening there later. All right, so the idea here is to say, okay, well, this is going to be a little bit harder to decipher than simply looking at unencrypted text. So it's one step in the direction of protecting your data. And I'm hoping all of you got to try that. How are we doing? Can I get some thumbs either up or down if you need more time, up if you've got it working? Thank you, Aaron. Thank you, Kevin. Looking good. Anybody need more time? Just give me a thumb down. Thank you, Sarah. Okay, it looks like everybody's on their way. Again, give me a thumbs down or a shout out if you need more time. What I'd like you to do now is simply take this same script. It's the last one I pasted in. So take this same script, the one that is encrypting. Just take that same script and copy it. Close serial on your other one that was the sniffer. And now we'll play the role of the intended receiver by loading the same script into the receiver's one. And now the assumption is that students have exchanged keys. And so if we now enter the same key in both, the students can continue to chat. And again, I'm using the key of 5 just to keep it obvious. And then what the students do is they also modify this script to display the ciphertext as well as the plain text. All right. Let's see here. So on that note, we go through and talk about how the function, the ASCII shift function is applied here, and all the details. And then next up is encrypting your app data. So this is another one where some encryption is added, and it's the countdown timer. So we'll have you guys try this one too. Okay, so I'm copying in the transmitter first. So there's the encrypted transmitter. And I'll copy that into 1 microbit. And then the receiver will copy into another one. Okay, here's the receiver script into your chat. Whoops. What? Is this too long? Paste. Yeah, it's not letting me paste that. Okay, so I have a script that's longer than the chat will let me paste in. So what I'd like to do instead is have you guys go to this page. All of you will have you go to this page and then take the transmitter script and paste it into one editor, and the receiver script and paste it into the other. Okay, so here is the page address. Okay. Okay, so if I enter the countdown start of 3 and then lift off. Okay, so this is working fine, and we don't actually see any differences right now. There's no way to tell that there's encryption going on in between. But there is definitely encryption because it's being encrypted on this end. Right here. So basically, the packet has been put together just as it was in previous incarnations. But the step that got inserted is to call so we start with a packet. It's got a string that contains the dictionary, and the packet is then sent to the ASCII shift function, and what comes back is the encrypted one, and the key is 5. On the other end, still have ASCII shift. The key is -5. And when it comes in right here, the first thing we do with the packet when it comes in is send it to ASCII shift with that key of -5. And then the rest is just the normal application. So once you've got this function up here, or as would be the case with real encryption in full computer Python, you'd be using an encryption module, and you wouldn't have to add this function. You'd just be calling a function that comes along just like the radio features and the microbit basic features. You'd be importing one of the encryption libraries. But at this level, we're just using ASCII shift. And so a thing you can try is monitoring the encrypted data. And again, so we challenge the students to put their keys on the keyboard and make this change. And so what we're doing here is that we're printing the packet before it goes out. And then we're also printing it before it gets decrypted. So let's go and try that. Oopsie, close serial. Close serial. So let's all go to our transmitter. And what we're going to do is add one line. Let's see here. So this is the packet before encryption. So we're already seeing what the packet looks like. Here's where the encryption happens. Here's where it gets sent out. So what we want to do is right here, print the packet again after it's been encrypted. Print packet, end quotes, colon, packet. So that's a way to give it a label. And I messed that up. Has to be a comma. I'll paste this into the chat in a minute. Okay, so that's what I wanted to see. So between packet equals ASCII shift and radio.send, we want to insert print packet, colon, in quotes, comma, and then the packet variable. Okay, I'm just about to paste that in case you need it. Copy. Okay, there it is. On the receiver side, so that this is the transmitter side right here. So I have 3 lines shaded. You'll be inserting that middle line that I just chatted to you. Then on the, and this is the transmitter side, then on the receiver side, this is decrypting the packet. So basically, if there's an incoming radio packet, decrypt it, print the decrypted version, then go ahead and do the countdown. So what we want to do is between line 30 and line 35, on this end, we also want to display the packet. And it's actually going to be that same string. It's just, and you just need to make sure that it's indented at the same level as the rest of them. And that also goes for on the transmitter side. You want to make sure that print packet is indented the same level as the lines above and below it, all of which are part of this while true loop that repeats over and over again. So again, use the same print packet on both sides. And you're going to be using it between receiving the packet and decrypting it on the receiver side, and between encrypting it and sending it. We'll print that on the transmitter side. So flash them both in, open serial, and I have to do it twice because for whatever reason, I see activity from the app that was running previously. Okay, maybe 3 times. Okay, so enter countdown start. I'll do the number 3. And then the message after countdown. You know, I don't remember what my encryption key here is. If it's 5, we'll be able to see it if we use, yeah, it is 5. We'll be able to see it if we use hello. That should come through as MJQQT. I'll add an exclamation point. Okay, so previously, before we added this, we didn't get to see the encrypted data. And here it's a little bit more, more challenging to figure out. Although, again, since I turned it into a straw man by using the key of 5 and the word hello, if somebody was interested in trying to figure out innately a brute force type of attack, which we'll be talking about next, they'd be able to do it because they'd notice that MJQQT right away. And then again, that would be if it was a sniffing attack. So if we used a different encryption key on both, flash, flash, open serial, open serial, 4, low. And now there's no MJQQT. It would be a little bit more difficult to figure out what's going on there. So what we just went through here, and well, there's a little bit more. There's a robot control version of this that I'll show you tomorrow. And essentially, the Cyberbot has been along for the ride the whole way. For those who have Cyberbot robots, it's just that Since we're only doing microbits in this one, I'm mainly focusing on the microbit portions of the lessons. Next up is brute force. Any questions, comments, or ideas before we jump into that? All righty, everybody keeping up? Can I get a few thumbs up? Or thumbs down, if it's the case. Excellent, thank you, Aaron. Thank you, Nada. Okay, oh, thank you, Sarah. Okay, I'm really glad that everybody's keeping up. And oh, Skyla, thank you. All right. Next up is brute force attacks and defenses. And so the first one, as with some of the previous examples, the first one uses the microbit display as opposed to the terminal. And this time we get to use the buttons as well. First off, we talk about some informational stuff, like how many different combinations 94 printable characters makes, and how the number of characters increases the number of possibilities of what your password is, which makes it much more difficult to brute force attack. And backing up just a little bit, Stephanie in the evening for a while was watching, was it Sherlock?
Yes, it was Sherlock.
Would you like to talk about this?
Oh, in cleaning out the garage, I found a number of combination locks that I had had around for a very long time and no longer knew the combination to of this type. And some had 3, some had 4, some were padlocks, some were bike locks. And so I would sit there and just try every combination until I figured it out so I could put them back into service. And now I have them all in one place unlocked. And then Andy explained, this is a brute force approach. Well, something to do while watching TV.
Yes, and indeed it was a brute force approach. And now, fortunately, I don't have a picture of my bicycle with this, otherwise I might be in deep trouble, huh? Okay, so that is brute force, essentially the essence of it. And so again, we talk about, am I zoomed in? Yeah, I'm way zoomed in. Okay. So initially we talked about just the most basic brute force attack idea that many of you and your students have probably tried from time to time when you forgot your lock combo. And then we have the idea of BitLocker and how the number of possible passwords increases multiplicatively as you increase the number of characters you use. And we also talk about some of the historical stuff, like the German Enigma machines and how there was an effort to crack that code, and it was very important during World War II. And then we move on to the an example of cracking a so-called bank vault. And this one came from cyber.org and is included here as a copy in order to stay in line with some of the material that they have. So let's try this out. I'll paste you in the transmitter and receiver. There's the transmitter. Oops. Got to make sure I've got it too. Okay, that's my transmitter. And then here we have the receiver. Okay, so I pasted you the pin pad transmitter already. Here is the pin pad receiver. Okay, so flash the transmitter, flash the receiver, and it simply open serial twice. And all right, so this is primarily on the microbit. And so you're going to want to find the one with the one with the dot in the bottom left corner. That's going to be your transmitter, is the one with a single light on in the lower left corner. And the way you pick a number is, and it's a binary. It's either a 0 or a 1. So you can press and release the A button to toggle between 1 and 0 as your number. And I need to remind myself of what the actual combo is. Okay, so it looks like, oh, well, we can figure out the combination from the, okay, so the actual pin on this vault is 011. So first of all, let's try, and this is what happens in the tutorial as well. Basically, I'll start out by pressing the B to accept 1. So I just typed in 011. I accidentally typed in correct combo. So okay, so when I press enter, oops. Oh, good. So 010 is the wrong combo. And that's what's in this microbit. And when I press the B button, we'll see an X in the receiver microbit indicating that no, that was not the right combo. So back to the transmitter microbit. This time I'll do 0, 1, 1. And I'm about to press the send, and we'll want to see what happens in our vault microbit. And we see a check mark indicating that that was the correct pin. So that's an example of using the microbit to as a mini vault or a locked pick. And it's also something that can have a brute force attack mounted against it. So next up, there's a script that mounts a brute force attack. And what this animation is showing here is the last few steps before the brute force attack succeeds. So it automatically goes through and tries all the different combinations from 000 to 111 if it had to get there. So it starts with 000, then 001, then 010. And then when it finds out that access has been granted, it stops searching. So this one you'll want to go ahead and put in your transmitter to see how scripts end up automating attempts to crack various encryption keys. Okay, I don't know if this one's too large. It is too large. Okay, so I'm going to have you go to this page and paste this script into your transmitter and watch it go. Whoopsie, sorry. Okay, so here's the page. Paste. So grab that script and put it in your transmitter. And flash it. Oops, I always do that. There we go. Flash. Okay, and then there's going to be an arrow on the microbit that's going to mount the brute force attack. And so that arrow is telling you to press a button to start the brute force attack. It's telling you to press the button A. And so when I press the button A, 000, 001, 010, 011. And when it got to 011, that was the actual combination. And so the transmitter found out that it had figured out the code and was successful in its brute force attack. And we do some fun things here. After explaining how it works, there's a randomized number, a randomized volt number. And then the next thing up is to talk about, okay, let's use decimal numbers. And so you can go from 0 to 6 in a column by using the A to count up. And so here's 3 to 4. And so it talks about how there are more combinations and it takes longer to crack the code. And I'm assuming you guys can see where we're going with this. I'll leave this activity for you to try on your own time if you're interested in doing so, because we have just a little bit of time left. And Stephanie, is there any chance, I'm sorry for springing this on you, do feel free to say no. I was wondering if before we end the meeting today, you could show them what the email is going to look like for being invited to join the learn.parallax.com educator account.
Well, you'll get one automated email from our system and you'll get another email from me. And I'll simply put at the top assessment material access.
Okay, so look for an email from Stephanie Lindsay that says assessment material access. And then is there also, I forget, it's like learn@parallax.com or something like that.
Yeah, there'll be instructions in the email on where to go and how to get directly to the material for cybersecurity.
Okay,
Yeah.
So I think that's going to be your primary homework for between, I'll just jump to that right now since I brought it up. Let's see here. It's no reply at parallax.com. So this will be the other email. So what
you may
again?
or may not get that email. Actually, some school districts
Filter
security
it.
systems prevent it from coming at all, which is why I send a separate email. And there will be a link to reset your password in the email I send. And if that doesn't work, no problem. Just let me know and we can get you in manually.
And also, don't stress if there's any delay on this, because although it's it's the way to get to the teacher resources that I'll be talking about on Friday, it's not part of the hands-on to actually go into the teacher resources yourself. I know many of you will as I'm talking about them and showing you how to get in, but it's not required. So if there's a delay and you don't get your, some of you will already have your educator account on learn.parallax.com. And so the homework for you will be to make sure that you can go to learn.parallax.com/user/login and log in successfully. And so try that and contact Stephanie. Will you want them to email you directly or education if they can't get into their account? Stephanie sounds like she might have stepped
Nope,
away.
I'm right there. I was muted temporarily, so you wouldn't hear me typing. Yes, you can do it either way.
Okay,
I'll
so
be sending an email to everyone one way or another.
okay, excellent. So look for an email from Stephanie, and then you might also get this account activation email from learn.parallax.com. And again, the homework will be to make sure you can log in if you already have an account, or to reset your password and make sure you can log in if you, following the instructions for Stephanie, if you don't already have an account and she just made one for you. All right, so with that, let's jump back to, and I'll send out a quick email about that too. With that, we'll jump back to not sniffing attacks, brute force attacks. And so let's see, what else do we want to talk about before the end of the session? You guys have been so quiet. I've gone through a little bit more than I expected to. Sorry about that. Let's see. All right, so we'll go with strategies to, yes, this is kind of cool. So here is, and I believe this one is just terminal. Yes, it's just terminal. So here is one to try where basically it slows you down, because computers can go pretty fast through a very large number of different combinations. And so this is a feature that you may have seen a certain number of times, where if you get your password wrong 3 or more times, then it tells you to wait for a certain period of time. And what that does is it makes brute force attacks more difficult to mount, because they can't a computer script can't simply whiz through all the different possibilities. Paste. Flash. Okay, so the correct pin is 324. And so I'll try 323. Access denied. 324. Oh, good. I got it. Access granted. Now, if I do it 3 times in a row, it's going to make me wait for an hour before allowing me to try again. And then here that is in script form. So it's kind of an interesting activity from the standpoint of improving the security of some kind of online vault. Now, then we talk about how ciphers end up being cracked through brute force attacks. And so let's see here. Yes. So what we'll do is we'll take the encrypted text WJCNU, or actually we'll go back and we'll have we'll use the happy, sad, angry, and the brute force script is going to grab one of those Caesar encrypted, and in this case it's angry, but it might be any one of the three. So what I need to do is get you back to the so that was back in share something personal encrypted. It says to do this in the checklist instructions, so I'm just getting the right text for you from memory just to make it so you can try it out. So here is the transmitter. So we'll want to do the transmitting of the different images, the happy, sad, angry that we did previously. So I just pasted that in, and we'll have you put that in 1 microbit. And then we'll go back to the brute force attack to try to crack a cipher. In this case, the Caesar cipher with an unknown key. Wait a minute. Oh, I apologize. Let's see here. Okay, I blew it. We have the transmitter and the receiver, and my from memory part was not working quite right. So forget about the thing I just pasted into you. Let's see if this will paste in. No. Okay, so this script is too long, so I'm going to paste you the web page, have you try it out. And so this is again transmitting encrypted happy, sad, angry values, and then a brute force attack so that students can see how a weak encryption key is very easily cracked with a brute force attack. So you want to do your transmitter in one and the receiver in another. Flash, open serial, open serial. Okay, so so my script received YGJ. Now yours might not have received that, but that's what my script received. And so it's going to go through, or now a human has to go through, and if they make the assumption that the Caesar cipher is being used, they can go through and scan through and find, hey, look, there's some data that can be deciphered, and it looks like the key is -6. And so even though we're sending encrypted data, now we can see that the strength of our, now students can see that the strength of their encryption key becomes more important as they end up reapplying the computer science concepts learned earlier to write these larger and more involved scripts. And we continue with an activity on creating more combinations and then strengthening your cipher with substitution and using a random cryptobit. So let's, we got a couple minutes left, so we'll just take a look here at a random cryptobit. So if you have something like this where you are where you start with an alphabet and then change your basically pick a unique corresponding character for each of your plain text alphabet characters. And then so we picked P, and then we picked T for B, and Q for C, and G for D, and M for E, and so on. And so this custom cryptobit does make the cipher stronger, much stronger, in fact. Instead of trying 26 passwords or 26 decryption keys, you end up doing 26 factorial decryption keys, which is a really large number that would be very difficult to figure out mounting a brute force attack. Of course, that's where some brains come in, where if you see 3 characters, you might deduce that it's the word sad. And so even this can be gotten around with some clever attempts. And then we go at the very end and challenge the students to go through and strengthen some of their previous applications, including Cyberbot navigation control with keyboard. And I believe the countdown timer is somewhere in here too. Oh, we're even doing the we start with share something personal. So that's the microbit part. And then here's the Cyberbot. And I'll show you some more Cyberbot stuff on Friday. So again, your homework is going to be to check the email from Stephanie and make sure you can get into your account at learn.parallax.com.
One thing, I am off tomorrow, so if you aren't able to get into that this afternoon, I will be able to help you Friday morning or Friday during class. And
again, it's actually not homework that you have to do for Friday, but I highly recommend it just so you can have it out of the way and know you have access when we talk about the educator resources. Okay, so that's it for today. Again, on Friday, we'll do some review, talk about malformed packets, do some Cyberbot robot demos. I don't know if we have somebody from cyber.org. I need to reach out for them to them. Otherwise, I'll find something interesting to do in its place. We'll talk about the educator resources, upcoming workshops, how to buy, questions and answers, and wrap up. So that's what's coming up on Friday. All right, and do feel free to stick around. So I'll do the usual sign off, but we'll continue to have some discussion afterwards for anybody who has questions, needs technical support, or has some comments. But that concludes today's installment of Cybersecurity with Python and the Microbit, and we'll see you again on Friday. And Stephanie, can you turn the recording off?